if you're here for probabilistic modeling and hope to hear about probabilistic modeling, you had your chance to leave. Now you're stuck with me. This is going to be very different from what you've heard earlier today and probably at other PyData meetings, at least compared to the one that I was at last time. It's going to be pretty high level. Mostly what motivated this talk was to give me a chance to talk about a domain of application that people don't necessarily think about that often, at least in data science, for deep learning-y stuff, and to talk about a random personal project that I've been farting around with. Okay, I haven't timed this talk, so if I run over time, just... Okay, I'm going to talk a little bit about linguistics, because how many of you know what linguistics is? A couple of hands. How many of you have done any linguistics? Oh my God, there was a couple of hands up. All right. I'll talk a bit about linguistics generally. I'll talk about what the heck vowel harmony is. I'll talk a little bit about neural nets, and then I'll talk a little bit about my project, and maybe it'll be fun. I don't know. Feel free to be critical. Okay, so what is linguistics? Broadly construed, it's the study of language. It breaks down into roughly 5 domains. You can be finicky. Semantics, we all sort of know what semantics is. It's about meaning. Syntax is grammar. It's how you put words together into sentences. Morphology is how words get put together. Phonology is about how sounds pattern in language. And phonetics is about the way you perceive and create sounds, right? Today, I'm mostly going to be talking about those levels, and in fact, mostly phonology. So, what does that mean? What is morphology? Morphology studies the composition of words. Morphemes, the things that morphologists care about, is basically the smallest meaning-bearing unit of language, right? So, a word like dog is sort of, you can't break it down into anything smaller, and it carries some meaning. A verb like tie is meaningful. But there are subword-sized bits that are also meaning-bearing, right? So like the prefix un means something. If you stick it onto the verb tie, you change the meaning of tie, undo or negate. The suffix s can mean plural in English, for example. So that's enough morphology for today. This is more of the same thing. It's just showing you how you can put morphemes together to create words, right? So the word untieable is a word in English. Native speakers will largely agree with me, and you can put the pieces together. And the meaning of the word untieable is transparently a function of the meanings of the subbits. That's morphology. What's phonology? Phonemes, the things that phonologists care about, is just the smallest discrete unit of language. They carry no meaning on their own. They're basically sounds, but not really. Something closer to the mental representations of sound. So whatever it is that we have in our minds that allow us to break down language into its smallest bits. Okay, so my pop quiz for at least native speakers of Canadian or American English. How many vowels are there? 2, 5, 5. Any other numbers? 12? That's pretty damn close. Depends where you're from. 9, maybe 10, maybe 12, depending what region you're in. One of the main things that a phonologist or linguist will tell you is that spelling is a very terrible reflection of speech sounds, right? So O-U-G-H in English can be uff or oo or o, right? So spelling means nothing. There are 5 alphabetical vowels, maybe Y, but there are way more than 5 English vowels. This is a chart with representations in the International Phonetic Alphabet, the other IPA, the better one. I won't go through all of these. These are words that differ, word pairs or triads that differ, again, ignore the spelling, in a single vowel sound. Beat, bet, or bit, bet. Wooed, as in to woo somebody. Would, cut, caught, depending on your, there's very few people in Canadian English that actually have that vowel. Pot, pat. It's all very interesting. Okay, so We've got sounds. Phonology is the study of how sounds pattern within and across languages. What is this? So intonation, what phonologists often call prosody, exists above the level of a phoneme. Sometimes they span several phonemes. And then there's some other stuff that I'm ignoring completely, right? So like Mandarin and some other Chinese languages have tones, right? So you can have the same vowel sound and with a rising or falling tone will mean different things. Those are phonemic as well. I'm glossing over a whole bunch of stuff. We don't have time to do a degree. Okay, so what is a sound pattern? What does it mean to study the patterning of sounds? One example is something called place assimilation. To assimilate is to become more like, and place, in this case, particularly means where in your mouth you articulate a particular sound. So, the word impossible, that's gonna kill somebody. The word impossible in English historically derives from the in prefix, which we see on incredible and inedible and whatever. And it reflects the fact that when you say impossible, the p of P gets pronounced at your lips, and this N, basically over the course of English history, turned into an M. It's reflected in the spelling in this case, but that's not always the case, right? So the second word there, believe me or not, when you say unbelievable, what you say is unbelievable, not unbelievable, right? So you have this real-time assimilation of that N sound into an M. Interesting. Other examples we can discuss. So that's one example of a sound pattern. Bear with me, I hate public speaking. Why did you agree to do this then? A possibly more interesting sound pattern for us today is so-called voicing assimilation. So in English suffixes, the plural suffix, how do you make a plural in English? Usually, you just stick an S on the end of the word. Cat with an S, dog with an S, it means more than one. Interesting, except that what happens is the pronunciation actually changes depending on whether the phoneme directly before it was voiced or not. So if you say cat, t, 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 you don't feel your vocal cords vibrating. If you say dog, g, 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 you can feel your vocal cords. Cats, dogs, but it's spelt the same. Similarly, in the English past tense, walked, jogged, voicing assimilation. The voicing of the morpheme assimilates to the voicing of the thing before it. So these are the kinds of things that phonologists care about. Maybe it's boring. I don't know. We got to stay busy somehow. All right. So what is vowel harmony? We just jumped to Linguistics 201. What you find in a lot of languages in the world, in a whole bunch of different language families, is restrictions on which vowels can co-occur in a word, right? So in Turkish, there are 8 vowels, and you can divide them into front and back vowels. And that corresponds roughly to where in your mouth your tongue body is when you pronounce them. And e, I, U, U, these are sounds that we have in Quebecois French. Like them, U like tu, A, O, U. So this is like a U, but with your lips unrounded, U, right? Front vowels, back vowels. What you find in Turkish, in native Turkish words, is that all vowels are either back vowels or front vowels, and there's no mixing of them. And in particular, what you find is that when you stick morphology onto the end of the word, the vowels change to agree in frontness or backness with the frontness or backness of the vowels in the stem. So you don't need to worry about what these mean. This is a locative case marker that means from or to. This means plural. This is third person. So this L vowel, R vowel, ND vowel means locative plural third person. And if I stick it on mal, I get malarinda. And if I stick it on kul, I get kulerinde. So the vowels change to agree with the vowel quality in the word. Cool. So essentially, this looks a lot like the assimilation that we were looking at previously, the voicing assimilation or the place assimilation. except it's interestingly non-local, right? It's something that skips over all of the consonants in between. It doesn't give a crap about the consonants. It goes and it finds vowels wherever they are and changes in backness or frontness to agree with them. Nifty. There's a twist. There's always a twist. Finnish, also a language with vowel harmony. Here are two roots that mean different things. We don't need to worry about it. This is another kind of case marker. You don't need to worry about it. The vowel alternates to agree. Cool, we've seen that. Turkish, boring. We're well versed in this now. But the vowel E in Turkish is transparent. It is invisible to the vowel harmony process, right? So here I have this word. Don't know what it means. Are there any Finnish speakers in the room? All right, I could have just made it up. Whatever it means, it's fine. O is a back vowel. So Finnish has front-back harmony the same way Turkish does. E is a front vowel. When I stick this same suffix, oh, it's a different suffix, sorry, different suffix. When I stick it on there, it surfaces with a back ah, not a front ah, even though the nearest vowels are front. So there's a wrinkle in there. You can pretend that it's not there. Phonologist will tell you it's fine. So essentially, this ah is getting its backness from the O that's all the way over here. So it's skipping over intervening front vowels to get its backness. So we say E, high front vowel, is transparent in Finnish. Cool. So all of this is stuff that kids learn and master by the time they're about 2.5. Nobody ever teaches them. They just produce morphophonemic alternations like friggin' magic. It's super cool. All right, enough of that. You guys learned a bunch of stuff that you didn't know today. Neural nets, artificial neural nets, deep learning, whatever you want to call them. There is a broad distribution of ages. Some of you know these by different things. Some of you are already bored of them. Some of you know them as the second best way to do anything, etc. What are they broadly construed? I don't give a crap about the brain. I do, I studied it, but for the purposes of this talk, I don't. It's a directed graph of computations, some that happen in parallel, some that happen sequentially, with information flowing from inputs to outputs. There's other kinds of stuff. For the moment, I'm gonna take this simplified view. A feed-forward neural net is a DAG. Without doing some hinky stuff with your inputs, it's hard to deal with temporal or ordered sequential kind of data. A recurrent neural network has cycles. Some computations depend on prior outputs. They are basically made to or can easily deal with temporal or ordered inputs. Neat. There's a bunch of things that were proved about them 20 years ago now that are really interesting. They're computationally universal, like most neural nets, blah, blah, blah. Who cares? A recurrent neural network, I had it on its side here so that the direction of input to output matched in both pictures. But it's not helpful because, all right. You can interpret or you can view a recurrent neural network. You can unroll it in time, essentially, and view it as so. Essentially what's happening here is we're saying this hidden unit or hidden layer, depending on your level of granularity, feeds some values out into the world, whatever's downstream, and back to itself. This only has one time unit on it, but really it's kind of across a bunch of times. So at time 0, some input comes in. My hidden layer calculates some value and sends it downstream, but also sends it back to itself, i.e. to itself at time index 1, and et cetera for however long my sequence is. Nifty. Yeah, that's what I said. Temporality is built in. All right. Yeah. So, again, 25-ish years ago, people were like, oh, if my sequential data has really, really long dependencies in it, these RNNs have a hard time learning those dependencies. And then we figured out that there's reasons for that having to do with the activation functions and whether or not gradients propagate well through time, yada, yada. And then somebody right around the same time, does anybody here know who Jürgen Schmidhuber is? or have heard of him? Yeah, all right. Lone troubled genius in Switzerland, with one of his grad students or postdocs, I don't know, was like, hey, we can do this cool stuff on the inside of an RNN and basically make the gradients propagate better. So for all intents and purposes, this is still just an RNN. I'm not going to go into the details. I'm not going to show the equations. I don't care. There's fancy stuff inside that helps the gradients propagate well and helps these learn. It's called a long short-term memory, and that name has always bothered me. I'm like, what does that even mean? Anyway, they can learn long-distance dependencies much better than traditional RNNs. They're still kind of an upper bound. And there are variants of these with more or fewer gates and some other different architectures. Some of you probably recognize these graphics. I ripped them off of Chris Ola's blog, which is, I think still, it's 4 years old now, and probably still the best explainer on LSTMs anywhere on the web. It's really good. These slides aren't posted yet. They will be after. Okay. More recently, actually, no, these existed a long time ago also. People were like, oh, maybe I can do something that looks like transforming one whole sequence into some other kind of whole sequence. And they're like, all right, I can just connect two RNNs together. These are unrolled in time again, quote unquote. So you feed in some sequence, encode it into some intermediate state, the last output of the hidden units on your input side, and then you feed that into a different network and you unroll it into something else. Neat. Not necessarily of the same length, and it turns out that people were very quickly able to kind of achieve state-of-the-art neural machine translation, among other things, with this kind of architecture. Already, they're kind of falling out of favor. There's other approaches that seem to do better and faster. These have problems with, among other things, parallelization because of the sequential nature of the data, and so they're not easy to train quickly, and blah, blah, blah. They're still neat. Right. Now used in many NLP-ish applications, although being displaced by other architectures. Are we all with me so far? Rad. I even got a thumbs up. Nice. All right. So the money question. Can a sequence-to-sequence network learn vowel harmony? A priori, no reason to expect not, given what we know about how those sequences work and what vowel harmony looks like. Why do we care? I spent way too much of my life worrying about vowel harmony. I did it in grad school. And I was like, oh, this seems like a fun thing to do on my own time. And independently, I know that other people have tried this going back to 1997, always with very simplistic toy data or underpowered architectures or blah, blah, blah. So I was like, hey, this seems like fun. So far, it's been fun. All right, so what did I use for my data? Is anybody, oh yeah, only a couple of hands went up for linguistics. The ACL, the Association for Computational Linguistics, has a whole bunch of special interest groups. One of them on natural language learning, and one of them on computational morphology and phonology. Every couple of years they get together and they do some sort of shared task competition. They release a data set and they're like, here, everybody go try and do such and such a thing. One of the things that they did last year was so-called morphological reinflection, which doesn't really mean anything. Just give me a word, give me some specification of its grammatical meaning, and now output whatever the correct form of it is with all of the morphemes and suffixes and affixes and whatever else, right? So if I want to train a neural net to just do pluralization, I gotta feed it some representation of cat and have it spit out cats, some representation of dog and spit out dogs, and some representation of, did I say that wrong? Foot and have it spit out feet, right? So it can't just be like, oh, put an S on it, because that doesn't always work. Man, man, feet, foot, ox, oxen, etc. So the data set looks like this. You have some kind of root form, what's called a lemma, sort of like a bare, uninflected form of the word. You have the inflected desired target form and some specification of the morphology. It's a noun, it's in the nominative case, it's singular, person. Anyway, the details of that don't matter, but it's a really nice data set. So there are lemmas, inflected forms, and morphological specifications for over 100 languages, of which, happily for me, a few have vowel harmony. I think about 8 out of the 100. I've only looked at a few so far. So there's Turkish, there's Finnish, Tatar is a language from the Far East, Kyrgyz, Hungarian. Super cool. So I get free data. Nice. Note that what I have is free textual data in an orthographic representation. Not ideal because, like I said, spelling doesn't always reflect phonology very well, but it's what I got. You get free data, you're like, it's good enough for a weekend project. As it happens, the orthography of Turkish and Finnish are much closer to the phonology than English is, so go me. Right, so, is that all of them? Yeah, all right. So what did I do? I started in Keras because it's what I was familiar with, and then for personal reasons, I switched. I wanted something with dynamic computational graph construction. I was like, ooh, I get to try to use PyTorch. And I fucking couldn't get it to run quickly to save my life. I don't know what I was doing wrong. I still need to go back and figure it out. But then I found Dynet, which came out of CMU and is insanely well engineered. It's so fast. The code is really nice. So it's all built in C++ with really nice Python bindings. Medium good documentation, but a lot of great examples that you can kind of crib, and isn't that how we all do stuff, right? Keras at the time, you had sort of like this static graph, so you had to build a specific graph, and then you have to do things like make sure that your inputs are all the same length, your input sequences, and you have to do zero padding, and it's all stupid, and I didn't want to deal with that. So Dynet, hooray. The documents are not bad. The code is nice, the examples are nice. It runs super fast on my CPU on this MacBook. Significantly faster than Keras did, and a good deal faster than PyTorch too, but that might just be because I'm an idiot. Remains to be seen. The general approach is easy. You define sort of a class for your architecture. There's a whole bunch of built-in stuff for LSTMs and RNNs and whatnot. You define your forward pass, you build a training loop, there's loss functions built in, and it does the auto differentiation, all of the stuff that we expect from our RNN packages. And I found a tutorial that does sequence to sequence stuff, and I was like, sweet. And then I just tweaked that. At this point, I've tweaked it a lot. That's ugly, but yeah. No, the Dynet code is open, it's there. It's just my stuff because I'm also submitting it to a conference. Yeah, Dynet is there and it's accessible, and I encourage you, if you like RNN stuff or deep learning stuff in general, to go check it out because it's nice. This is kind of terrible. You don't need to really worry too much about this. My general method of operation for this kind of stuff now, when I'm doing DL-ish explorations of something that I care about, is to make heavy use of the argparse module, which I really love, because I can code in subparsers, one for training, one for predicting. I can train and stave a model, and then I can load and predict with it, and I can write a bash script that will let me iterate over all sorts of parameters, right? So in training mode, there's a bunch of stuff that I wanted to care about. Some of this won't make sense, but I can specify my test and validation splits. I mean, it's just, they're command line arguments, right? What do you care about? Do I want to use the morphology? Which language? Where's my data set? How big is it? What's my data architecture? So I can script a whole bunch of stuff in a bash script, and I can just set it up and let it run for days or whenever I need to work again. This is my work computer, don't tell my boss. Nice. Okay, so what have I done? Did I see a hand go up? No? All right. What I cared with, at least initially, is I want to see if I can do something with a sequence-to-sequence architecture. I'm going to start with the simplest architecture I can. So, single layer LSTM on the encoder and the decoder side, roughly the same size, super basic, kind of like dumb. And then what are the things that I care about? The main architectural hyperparameters, there's a bunch more stuff, but how do I encode my inputs and outputs? Do I use embeddings? And how big is the RNN layer? So I'll say a little bit more about that, I think. What have I tried so far? So that data set for each language has 3 data sizes that they released, 100, 1,000, and 10,000. So basically they wanted to test everybody, how good is your system at doing morphological reinflection if you just give it 100 pieces of data. Everybody sucks, because what are you gonna do with 100 pieces of data? Anyway, so I've got a few data set sizes. I tried a few embedding dimensions. The vocabulary here is obviously much smaller than if you're doing full-on NLP over words, right? My vocabulary is the number of phonemes in the language, an upper bound of 50-ish, right? So I don't need massive embeddings. I don't need 300-dimensional embeddings. I tried some pretty small ones. Weirdly, they don't do anything, right? So I actually wound up doing better with just basic one-hot encodings on the input side than with embeddings. I have a separate paper with somebody that was actually accepted at this year's SIGMORPHON where we look at what you can do with phone embeddings. It's neat. And I tried a few different dimensionalities of on the RNN layers. So I'm talking fast. How am I doing for time? All right. I'm almost at the end. So okay, so how does this thing do? Terribly on the small and medium data sets, right? So that's 100 or 1,000 items. I just picked a representative graph. They all wound up looking like this, right? So this is the loss on the validation set. This is the loss on the training set. This is exactly what you don't want your RNN to do, or anything, any of your data science or machine learning models. Yeah, so in this particular graph is the medium data set, medium sized. This 796 here is because I had to split out my own validation split with 128 DRNNs, but they all looked like that. Boo. But with the 10,000 item data set, it learned. And I looked like that, which is cool. So this is a fair question, and I will kind of touch on it in a moment. So clearly I learned something here in a way that I wasn't previously. How exciting. There still comes some kind of generalization gap, which is not that surprising. The validation set isn't, like they're from the same distribution, but they're not exactly the same. Plus, so the way I was training this thing was feeding in one phoneme at a time and having it reproduce on the outputs with the proper inflection, right? So what I care about is that it learns the vowel harmony, learns how to match up the vowels the way it's supposed to. What I'm also asking it to do on the loss, though, I was just collecting the loss over all of the outputs, is getting it to reproduce, like to learn the consonants of the output suffixes as well. And I think I just didn't have enough data, right? So I'm pretty sure that this generalization gap is just because I asked it, I'm measuring it against stuff that I'm not asking it to learn, really. I don't know if that's the right way of putting it. So anyway, that doesn't really matter. It learned, I was happy, it was cool. But then Finnish has this transparency stuff, right? Where there's some vowels that are transparent to the harmony process. And I couldn't get any architectures to learn with up to 10,000 data items, given the data that I had, given the variations on the architectures that I tried. And it's surprising to me because it's really not that hard of a problem, right? I'm asking the net to learn that this particular phoneme should just be ignored on the input. This particular encoded input should be ignored when you're calculating the outputs. It doesn't seem like a hard thing, and it was surprising to me, and honestly, I still don't really know what's going on. So just to answer your question, these graphs are loss graphs. I was tracking the loss, but I was interested in a couple of things, right? So I was looking at the accuracy, and when I say accuracy, what I meant was phoneme for phoneme match on the target, right? So that accuracy measure is pessimistic because I'm asking for matches on the consonants, which really I don't care about. All I care about is that it learns how to do the vowels right. So I'm using an aggressive accuracy metric. It is what it is. And then I was interested also in Levenstein distances, right? So like how many of the consonants does it get wrong? Yeah?
Just as a question, so when doing
So
So that is to say, if it is this vowel, and if the ground truth is this vowel and not some other vowel, and you predict it to be that vowel, then it's correct. But if you predict it to be one of the other set of vowels, it's not
right.
correct.
So
Or a baseline accuracy would be one, by random guessing, you would expect 1 over how.
1 over the size of my vocabulary. Yeah, yes and no, right? So that's how I was computing the loss on the outputs, and that's not like, so this accuracy is an eval metric that wasn't built into the net that I just checked myself, and what I was doing was basically taking the max, whatever, the max probability output, assigning that class to it, and then for the entire sequence, checking if the whole sequence matches. It's a 1-0 loss on the entire sequence compared to the targets, right? So,
Sorry, one other.
yeah.
If that's okay. When you take a model that is evaluated, a baseline model, not random guessing, but some other baseline statistical model that is evaluated using the exact same accuracy metrics, what's the range of performance that you obtain?
That's an excellent question, and if I were a responsible data scientist, I'd be able to tell you. Don't tell my boss.
It's all fun.
That's the spirit. Anyway, so these are sample outputs. It doesn't really matter. So these are all front vowels. This is a mix of front and back vowels. This is with the target. I swear I'm trying not to tear down your building. So you can see that it kind of learns the vowel harmony, right? There's like, it reproduced the root, but then there's like weird repetitions that are part of the root. So it's not great. This is just one sample run on my best performing Finnish net. And, you know, I mean, in this case, it's obvious, right? My validation loss is going off to infinity. Maybe there are versions of the architecture that I could have just left training way longer that would have done better. That's not what's happening here. This is called the to-do pile. Some of it I've already started. Obviously, rule number 1, find more data. I had a bunch of free data. Finding annotated data of this variety is actually really hard. So the people, the SIG NLL and the Sigmorphon people scraped all of Wiktionary to put together their data sets, which is probably one of the best free sources for this. There is a consortium called the LDC, the Linguistic Consortium, and you can get all sorts of amazing data from them, but they'll ask for 3 pints of blood, so I don't want to pay them. So I don't know. If anybody has ideas where to find cool textual data on inflected morphological forms in vowel harmonic languages, hit me up. So as I mentioned, this is sort of discretized textual data, and I'm interested in seeing whether or not some kind of architecture could learn this on actual acoustic data. So I actually have a corpus of spoken Turkish with orthographic and phonemic representations. I haven't started on it yet. There's a bunch of stuff that you have to do with acoustic data to make it work well if you don't have Google's compute resources. Okay, so more metadata, more powerful architectures. I've started looking at BILSTMs and maybe multi-layer RNNs on the inputs and outputs, or, and this is maybe the obvious thing, incorporating some kind of attention mechanism. I suspect that that's going to render the problem completely trivial, right? Because as soon as I can get it to look at the whole input sequence, I think that the transparency issue will just cease being problematic. And maybe that's interesting in and of itself for me when I'm wearing my linguist hat. Maybe there are better loss functions than the one I'm using. Maybe there are evaluation metrics that are more revealing. I'm working on it. We'll see. And that's it. There's no time for questions. You can talk to me after the break, blah, blah, blah. I'll come and find you after the break. Unless you want everybody to hear your question. Do we have a couple of minutes? Yeah. All right, you first, then you. So the input is the root of the word, the base form of the word, and some representation of the meaning specification, the morphological specification. Is it plural? Is it in the one case or the other? Is it singular or nominative, third person, first person? And the output is the full version of the word, right? So I give it the base word and some semantic representation, and what I want on the output is the full form of the word. Yeah, yeah, I totally can. And right, oh, hold on, right. Let's go with this one, right? So my input is, for example, some representation of this root, M-A-L, however I have it encoded, some representation of this specification of meanings. What they mean doesn't really matter, plural, third person, locative case, and this is my desired output.
Okay, so it's the same word, just
Right, so it's the same root, but with the relevant suffixes or whatever phonological changes that are, right, exactly. Hold on, you were next. No.
You have one suggestion. I think what to do is basically going through it once, then basically put an encoding of that, and then basically put the data into again with that encoding.
So encode the root first, and then stick on the morphological specification and feed that to the, yeah, that's as good a thing as any. I'll try that. First Alex, then you.
I don't think you mentioned this, so I'm curious if you've tried any transfer learning techniques, such as using some pre-trained character embeddings and then transferring over those embeddings to your task.
So I didn't. The question was, did I try any transfer learning type stuff like pre-trained character embeddings? So I didn't, and it makes sense to do that, and that would probably get me further along than just training the embeddings from scratch on very little data, which is probably why they didn't make any difference for me. I could do something as simple and stupid as just running word2vec over the characters. So independently, phonologists believe that the way we encode a lot of these phonemes or phones is actually context dependent, right? So we encode the p at the beginning of a word differently than, like, the p in pat versus the p in spit are actually encoded differently in our brains somehow. And so something more like Elmo Bert style contextual embeddings would probably give me a little bit more leverage. Like, all of the libraries to code those, to train those things from scratch is a pain in the ass. So yes, I'll get to it eventually, and I haven't yet. You. Yes.
I'm not expert in this kind of deep learning.
Right.
Work with image processing.
Okay.
But this seems to me like a kind of that you are trying to force the word to be in some specific structure. So maybe, I don't know, I will give like a crazy idea that I have right now. Maybe if you, in the Latin representation, you feed some kind of neural network that will act as a conditional network to to feed that kind of features. I would say the log, the TL, or the third person.
Right.
Like condition to the representation, to the generation that will do the RNN. So I don't know if that makes sense.
I think it did. So are you talking about like training a side or parallel net to learn representations of these?
Something like that, exactly. And feed that in the
Feed that in parallel or maybe downstream or, yeah, that makes sense because I didn't do that. I just did the stupid thing.
like conditional GANs.
Oh, okay. Okay, all right. Yeah, that makes sense. Was there another question? Hold on, you first. You already asked one. I didn't, right? So I didn't do, I was like, I want to do the stupidest possible thing, and attention is on my list of things that I should try. And like I said, my expectation at this point is that attention will just be like, whatever, this is easy and stupid, and it'll just learn everything, and I'll be like, well, that was unsatisfying, but, you know. Yes?
Well, I don't know, is it there is some Google Translate service, basically can translate into any language.
So, I mean, so yeah, but what it does is it gives you the orthographic outputs, right? Which, granted, in Turkish and Finnish are closer to the phonology, but I don't know that I trust it enough to use that as a source of data. It's better than nothing, though. So maybe as a cheap source of data augmentation, that makes sense. Yeah.